Yes, sir.
Yeah, fine. Okay. So yes, we are discussing about virtualization, and let me have a glimpse on the same. So the last class that we had discussed about uh, Xen architecture, that is Xen hypervisor. So as usual, then we have to have, in order to make the environment to be virtualized, then uh, we have to have hypervisor, okay, or virtual machine monitor, right? These two. So on the name of hypervisor that I had discussed, that one of the type of hypervisor that is provided by the Xen architecture. We can call this hypervisor developed as Xen architecture. So what is the similarity happened with the Xen architecture? Simple thing. So as usual, it is a open source program, right? As I told you, developed by Cambridge University. Then what was the logic? As usual, that we had hardware devices as the bottom layer, right? And second layer, it has the Xen hypervisor, okay, this one. And we had different types of domain applications, like starting from domain 0, right? And it has its own applications. And this is Xen Linux, operated on Linux. This is the second one, okay. And the third one was Xen Windows, okay. Why? Because this Xen hypervisor installed, so that's why that we are naming as Xen especially, okay. That's why. So what happens, as usual, this is called the domain 0 application, and these are the other type of operating systems installed, right, on the hypervisor. So what happens, like as I told you, the guest operating system which has the control ability, the guest operating system which has the ability called domain 0. So it has the control over all the guest operating systems, and the others are called domain U. We can call this is for utilization or user domains. You can call. So these are the user domains, and this is the domain 0, which has the control over the all user domains, right? And where here domain 0 is a privileged guest operating system of Xen, and it is first loaded when Xen boots without any file system drivers being available. So domain 0, especially this domain 0 is designed to access hardware directly. Please mind this point. Domain 0 is designed to access hardware directly and manage the devices. So therefore, one of the responsibility of domain 0 is to allocate and map the hardware resources for the guest domains like domain U and others. So for example, Xen is based on Linux, and its security level is up to, but we have 3 security levels: C1, C2, C3. Okay, so up to C2 that we are defining, and its management virtual machine, okay, is named domain 0, which has the privilege to manage other VMs implemented on the same host. Okay, so if a domain 0 is compromised, so I'm speaking with respect to the security. If domain 0 is compromised, the hacker can control the entire system. So in the virtual machine system, security policies are needed to improve the security of domain 0. So if we improve the security of this particular domain 0, automatically the control policies will be controlled. All the control policies related to the Xen Linux, Xen Windows, and other operating systems can be controlled, right? So I can mention one important point here, that say domain 0 behaving as a virtual machine monitor, say example, okay, allows a user to create, copy, save, read, modify, share, migrate, and roll back VMs as easily as manipulating a file, which is flexibly provides tremendous benefits for the user. So traditionally, say if I speak, traditionally a machine's lifetime can be envisioned as a straight line where the current state of the machine is a point that progresses monotonically as the software executes. So during this time, configuration changes are made, software is installed, and patches are applied. Simple reason. Okay. So what I want to give you a kind of information here is that the Xen hypervisor is different, a different type of hypervisor as compared to other hypervisors. Why? Because this is developed by this person. So that's why the name is given as Xen, where that different types of domains have been created, and one of the domain which is installed, right, as a first domain called domain 0 takes responsibility and control over the all other domains, user domains created for applications. So this is the difference among the Xen hypervisor and other hypervisors. So I'll come back. Okay. So let me discuss the types of virtualization. So as usual, I'll start with the CPU virtualization first. Okay, CPU virtualization. So in order to make the environment, that we must and should have the hypervisor, type of hypervisor and something. Okay, yeah. So what happens here? Say as usual that I had discussed about cross 86 hardware virtualization. Say that if I speak about cross 86 operating systems, they basically are designed to run directly on, as I told you, to run directly on the bare metal hardware. So they naturally assume they fully own, say, the computer hardware. So say example that let me speak. So here, this is the host computer system hardware. This is the host computer system hardware. Okay, now I have say these many number of rings, my dear friends. Say ring 0, ring 0, ring 1, ring 2, say ring 3. Okay, totally 4 rings, where this contains operating systems. Okay, and I'm not naming ring 1 now. Okay, and I'm also not naming ring 2. Now ring 3 is user apps, represents the user applications. Simple. So there is a possibility that operating system communicates with the host computer system hardware, and user applications can communicate with the same. So this is this one. Okay, this is called direct execution of the user and OS request. This is the direct execution of the user and operating system request. So this is the concept. So this is called cross 86 privileged level architecture without virtualization. So here see no virtualization concept means or layer has been installed. Simply, so in a ring 0 manner, that operating system concept is installed. This is the host computing system hardware. Simple operating system. These two rings are quite free now, and from the ring 3 is arranged as a user application. Now the operating system is directly communicating with the host computer system hardware, and again user applications are communicating with the host computer system hardware. So this is called direct a privileged level architecture without virtualization. So let me speak now. So as shown in this figure, okay, the cross 86 architecture offers 4 levels of privileges known as ring 0, ring 1, ring 2, and ring 3. Okay, ring 3 to operating systems and applications to manage access to the computer hardware. That's it. So while user applications typically run in ring 3, the operating system needs to have direct access to the memory and hardware and must execute the privileged instructions in ring 0. In ring 0, why? Because without operating system, that no user application can utilize the same. Okay, so this is the way. So what I mean to convey here is that virtualizing cross 86 architecture, virtualizing this cross 86 architecture requires placing a virtualization layer under the operating system, which expects to be in the most privileged ring 0, I would rather say. okay, to create and manage the virtual machines and virtual machines that deliver shared resources. So further complicating the situation, some sensitive instructions can't effectively be virtualized as they have different semantics, okay, when they are not executed in ring 0. Here, that if you want to make this environment as virtual environment, then definitely that we must and should arrange the virtualization software framework here itself. Okay, here itself. This is the part. Okay. If it is so, the difficulty in trapping and translating these sensitive and these are the privileged instructions related to hardware, and that VMware utilizes the instructions on the name of sensitive instructions. Okay? So the difficulty in trapping and translating the sensitive and privileged instruction requests at runtime was the challenge that originally made this particular cross-86 architecture virtualization look impossible. Okay, so here VMware resolved the challenge. The VMware, okay, virtual machine, VMware framework resolved this challenge in 1998 itself, developing binary translation techniques. Let's see that I'll discuss. Okay, developing binary translation techniques that allow the VMM virtual machine monitor to run in ring 0 itself. Okay, in ring 0 for isolation and performance, while moving the operating system to user level ring in here, user application, user level ring with greater privilege than applications, right, in ring 3, but less privilege than the virtual machine monitor in ring 0. So while VMware's full virtualization approach, I'll discuss this, while VMware's full virtualization approach using the concept called binary translation, means two-way, binary means two-way. Binary translation is the de facto standard today based on the VMware's 20,000 customers installed based on base and large partner ecosystem. So the industry as a whole has not yet agreed on open standards to define and manage virtualization. So each company developing virtualization solutions is free to interpret the technical challenges and develop solutions, say with say varying strengths and weaknesses. So I'll discuss. So as as I'm going to clarify in the following manner, 3 alternative techniques now exist for handling this. Say if I arrange the VMware, then it will become sensitive instruction execution, and this is the privileged instruction execution. So these 3 techniques now exist for handling sensitive and privileged instructions to virtualize the CPU on this particular cross-86 architecture. So we have not virtualized it. Okay, so I'll discuss the concept now. Simple reason. Right, so I'll start with the full virtualization first, then after that I'll come back. So as usual, so what the concept of full virtualization says, my dear friend? Full virtualization, simple thing. So with full virtualization, basically, non-critical instructions run. Non-critical instructions run on the hardware directly, okay, directly, while critical instructions are discovered and replaced with traps into the virtual machine monitor to be emulated by the software. So both the hypervisor and VMM approaches are considered full virtualization. So why are only critical instructions trapped into the VMM? This is because the binary translation can incur a large performance overhead. So non-critical instructions do not control hardware or threaten the security of the system, but critical instructions do so. So therefore, running non-critical instructions on hardware not only can promote efficiency, but also can ensure system security. This is the point. So what is the question? The alternative techniques for handling sensitive and privileged instructions on cross-86 architecture. So I'll discuss the first concept as binary virtualization, sorry, full virtualization, this concept. Full virtualization with the binary translation. Please, binary translation. Binary translation. See what this concept says about. Yeah. See.
Excuse me, sir.
Please tell me.
Sir, could you please explain critical instructions once again?
Yeah. See, so with full virtualization, non-critical instructions run on the hardware directly. See here, I have not mentioned about any kind of non-critical instructions, right? I mentioned about the critical instructions and the privileged instructions. Okay, clear? So the non-critical instruction concept may come. Why? Because non-critical concept that may be existing means maybe existing with the virtual machine monitor that which we have installed here, right? And it may also come, they may also come from other rings as well, that I have not mentioned any kind of application here. So my concern is about only the virtual machine monitor. If the virtual machine monitor concept is installed, means maintained here, then we can consider the instructions coming for managing the activities of host operating system or critical instructions. Okay, and where the user applications are given some kind of privileges. So we call it as privileged instructions. Means simple a kind of kernel operation on the name of operating system, right? So I'm speaking beyond this one. Say I have not mentioned whether the non-critical instructions are existing with VMM or and the non-critical instructions are existing with the user applications as well, right? They may come from other applications as well. So with full virtualization, non-critical instructions, what we do, run on the hardware directly. Why? Because there is no limit as usual. Why? Because we have limited the privileged instructions, right, which must and should run on the host operating system, as well as the critical instructions of the particular VM virtual machine monitor can run on the host operating system hardware like this. But we have not mentioned about any kind of non-critical instructions here. So here we need to consider the concept of non-critical instructions, which may cause or may not cause the overhead of the particular application. So that's why with full virtualization, basically non-critical instructions run on the hardware directly, while critical instructions are discovered and replaced with the traps what into the this one VMM concept, to the VMM to be emulated by software. So if VMM is not there, then there is no concept of emulating the critical instructions. So both the hypervisor or and virtual machine monitor approaches are considered full virtualizations. Means even if we consider VMM or hypervisor, there may be a scope or there may be a chance that non-critical instructions can also or may also consult or contact or may work with the host operating system. So that is the meaning. Okay, so that both hypervisor and our VMM approaches are considered full virtualization. So in this case, the non-critical instruction concept can also be considered. But as I told you, that why are only critical instructions trapped into VMM? This is the question. The answer was, this is because the concept that which we are going to discuss can incur a large performance overhead. So non-critical instructions do not control hardware as usual. So they may come directly only for execution. So there is no control. Given for the non-critical instructions to manage the activities of host operating system. Why? Because the host operating system has already gone under the control of this particular VMM or hypervisor. Only critical instructions can manage. So non-critical instructions do not control hardware or threaten the security of the system, but critical instructions do. That is the reason. So running non-critical instructions on the hardware not only can promote efficiency, but also can ensure the system security. So there is no harm. This is the meaning that I want to convey. That's it. Fine now? Yeah. So let's see that how the binary translation can incur the overhead during the application. Why? Because the critical instructions are only it's given the chance to run and manage the activities of host operating system. So I'll discuss this concept by giving a pictorial representation. So I'm changing this modality now. Okay. So simply I wrote host operating system, right? After that, only operating system. Now we'll do with the level of other full virtualization using binary translation now. So this is host computer system hardware. Okay, host computer system hardware. Now, as I told you, this is ring 0. Now, instead of taking only the operating system, what we do in the ring 0 premises, right? We install VMM or hypervisor. Okay. Now, ring 1 become guest operating system. Ring 1 becomes guest operating system as usual. So now the ring 2 is still empty. Okay, this is given a empty slot given for other application, I believe. And ring 3 is only for user applications. Okay, see now, as usual. So what we had in the last CPU virtualization concept. So there is a communication, direct communication from the operating systems and user application as well. Now the concept has been increased. So as usual, we have the communication, direct communication, right? Direct communication from the guest operating system to the host operating to the hardware, and this one as well. This is the modality we had, no change. Now, apart from this, that we have a direct communication with VMM to the host operating system as well, means to the host hardware as well. So what it means, like just now I told you, know, that if we install VMM, then the critical instruction may cause the increase of overhead. Okay, so how we are going to change the modality? This we call as simply what we do. So instead of taking the individual directions from guest operating system to host hardware and VMM to hardware, what we do, see, we have the communication now. We have the communication from guest operating system to VMM, and again from VMM to host hardware. Now this concept is not there. So there is no direct communication from guest operating system to host hardware, right? Now we had the communication through communication from GOS, guest operating system, to host hardware is through VMM. So this is one, right? And this is two. And there is a direct communication, right, in the form of privileged instructions can be communicated with the host hardware. Now let me speak about this one. So this concept where GOS to VMM and VMM to host hardware, we call it as binary translation of operating system requests. Best binary translation of operating system requests. Now, as usual, this is the direct execution of user request. Direct execution of user request. No, right? See, now let me give the modality. This is the binary translation approach for x86 virtualization. See, VMware can virtualize. Now we have installed the VMM layer. So VMware can virtualize any x86 operating system using a combination of this binary translation and direct execution techniques. So this approach, which is depicted, say, in this figure, translates simple kernel code. This is the operating system primitive, kernel code, to replace non-virtualizable instructions with new sequences of instructions that have the intended effect on the virtual hardware. Let me repeat, my dear friends. So here in the x86 CPU virtualization, that we have not taken the concept of VMM. Now we are taking on the name of first concept, that is called binary virtualization. What it does here, this approach means translates the kernel code to replace non-virtualizable instructions. We have replaced with new sequences of instructions that have the intended effect on the virtual hardware. So meanwhile, the user level code is directly executed on the processor of the high performance virtualization. So each virtual machine monitor provides each virtual machine with all the services of the physical system, including a virtual BIOS, right? Virtual devices and virtual memory management. So this combination of binding translation and direct execution provides full virtualization, as the guest operating system is fully abstracted now, means completely decoupled from the underlying hardware by the virtualization layer. So the guest operating system is not aware it is being virtualized and requires no modification. Please, this is the point I'm mentioning here. The guest operating system is not aware it is being virtualized and requires no modification. So full virtualization is the only option that requires no hardware assist or operating system assist to virtualize sensitive and privileged instructions. So the hypervisor translates all operating system instructions on the fly and the caches the results for further use, while user level instructions run unmodified at native speed. So there is no change here. There is no change, but there is a change. Why? Because here the kernel, a separate kernel code is executed by the virtual machine monitor. So finally, full virtualization offers the best and security for virtual machines, and also simplifies migration and portability, as the same guest operating system instance can run virtualized or on native hardware. So VMware's virtualization products and Microsoft Virtual Server are examples of full virtualization. So this is the full virtualization with binding translation. This is called technique 1. This is called technique 1. Okay, so let me increase the let me discuss the another concept of type 2 here. That under the category of full virtualization, right, we have another modality that is called, this is technique 2, we can call. The first one was technique 1, that is binary translation. This is now operating system assisted virtualization or para virtualization. What is the difference between virtualization and para virtualization? Right, the scope is given for the guest operating system to communicate, right, in the full virtualization. In the para, that no means the limited actions will be there for whom? That is for guest operating system. So this is the meaning of para virtualization. Simple, my dear friends. Say what I do here. The para virtualization approach to cross 86 virtualization I'll discuss here. See what happens here. Here I will make the guest operating system itself as para virtualized operating system. What happens? See, here I'll take the concept of virtualization as usual. This is my host computer. Okay, host computer with the required system hardware. Okay, now this is my virtualization layer. As usual, means installing of VMware hypervisor. Okay, this is virtualization layer 2. Now, what I do in ring 0, I'll make the guest operating system as para virtualized guest OS. Okay, para virtualized guest operating system. So ring 1, I'll make it empty. Okay, guys, no change. Now ring 2 also becomes empty. Now ring 3 is containing the user applications, user apps. No change. Now ring 2 is quite empty now. So what happens? See the previous slide. So we have utilized ring 1 for guest operating system and R0 is for VMM. So what we did? So under the ring 0 guest operating system, that we have installed the virtualization layer. Okay. Now, as usual, so I'll continue the process of the same. What I do, let me maintain the flow. So in order to have the communication, the guest operating system will perform the communication with the virtual layer, and the virtual layer will communicate the preferences of guest operating system to the host hardware. This is one. And as usual, there is a direct communication from the user apps towards the system hardware. So this is the direct communication that I'm not discussing about. Now, see here, I'll discuss the concept that in what way the communication happens through the virtualization layer, right? From GOS to hardware. This is called this is happened in the manner of hypercalls. We call it as hypercalls. Hypercalls. Hypercalls to the virtualization layer replace non-virtualizable OS instructions. Please mind this point. Why? Because we have installed the virtualization layer, right, under the part of ring 0, where that we have discussed the concept of this one. Okay. So we have not made the provision for the virtualization as a separate ring. So this is combined. The virtualization is combined with the GOS. No. Now what happens here? Here hypercalls to the virtualization. Hypercalls to the virtualization and a layer replaces non-virtualizable. Virtualizable in the sense sensitive instructions. No. Non-virtualizable in the sense what? Non-critical instructions, right? Replaces non-virtualizable operating system instructions. So what the non-virtualizable operating system instructions contains? These instructions are non-critical instructions, non-privileged instructions. So right, so based on this concept, that let me give the description now. See, so yeah, just meaning that as actually this para, the word para came from Greek word, my dear friends, right? What it says, say the para means beside, with, or alongside, means given meaning as alongside virtualization, you can call simple meaning. No, so here para virtualization refers to communication between the para virtualization refers to the communication between the guest operating system, between the guest operating system and the virtualization and the hypervisor to improve performance and efficiency. So para virtualization, as shown in this figure, involves modifying here this one, modifying the operating system kernel, modifying the operating system kernel to replace non-virtualizable. So if we replace the non-virtualizable instructions, it will become virtualizable. So the communication will become more sophisticated, right? So because of this reason, this particular para-virtualization involves modifying the operating system kernel to replace non-virtualizable instructions with hypercalls. Non-virtualizable instructions with hypercalls that communicate directly with the virtualization layer hypervisor. So here the hypervisor also provides hypercall interfaces for other critical kernel operations, such as we have the memory management. Okay, this one, memory management, interrupt handling, and say timekeeping sequences. This is the one. So this is one. Now, how here the para-virtualization is different from full virtualization? Again, here the para-virtualization is different from full virtualization, where the unmodified operating system does not know it is virtualized, and sensitive operating system calls are trapped using binary translation. See, using binary translation. This is the way. So the value proposition of para-virtualization is in lower virtualization overhead, but the performance advantage of para-virtualization over full virtualization can vary greatly depending on the workload. Say, as para-virtualization cannot support unmodified operating systems. Example, if I consider Windows 2000 or Windows XP, okay, its compatibility and portability is poor, very poor. That's why the versions have been different versions have been developed and updated. Okay, so para-virtualization can also introduce significant support and maintainability issues in production environments, as say it requires deep operating system kernel modifications. So best example, the open source Xen project is an example of para-virtualization that virtualizes the processor and memory using a modified Linux kernel, and virtualizes the input output using custom guest operating system device drivers. Right? While it is very difficult to build the more sophisticated binary translation support necessary for full virtualization, modifying the guest operating system to enable para-virtualization is relatively easy. Clear? So VMware has used certain aspects of para-virtualization techniques across say the VMware product line for years in the form of VMware tools and optimized virtual device drivers. So the VMware tool service provides a backdoor to the virtual machine management layer or hypervisor used for services such as time synchronization, logging, and guest shutdown. Now, what I mean to say here is that it is important to note for clarity that the VMware tools service and the device driver are not CPU para-virtualization solutions. Why? Because CPU para-virtualization doesn't include the concept of VMM, no, here, right? Virtualization layer, because of that reason. So in this way, say looking forward, say for example, that VMware is helping develop para-virtualized versions of Linux to support proofs of concept and product development. So this is the way. So in this way, the technique 2, that OS assisted virtualization or para-virtualization, has been described. Okay, so this is happening with respect to the modification, operating system kernel modification of a guest operating system through the virtualization layer. So this is the concept involving in the form of para-virtualization. Now, if you come to the technique 3, first one is the binary translation. Second one is the operating system assisted virtualization or para-virtualization. Now the third one is completely hardware assisted virtualization. Hardware assisted virtualization. Please just listen this. Right. So no changes that I'll be making here. Now again, I'll replace the concept, means I'll come back to the actual combination of binary translation. Okay, binary translation, but I want to make this translation as without binary translation. So this is the difference. So without binary translation, it seems and looks like binary translation, but the concept involved here is without binary translation. Okay, so I'll depict this one. Let's illustrate here. Just see. So as usual, I'll take the combination of host hardware, host system hardware. Okay. Now I'll consider this virtual machine monitor again, but I'll make some changes here. See, so again, this is ring 0, my dear friends. Ring 0, which is a pure guest operating system design. Okay, ring 1, nothing. Ring 2, nothing. So this is the empty slot given for other emulating other parts of applications. Now ring 3, as usual, it contains the user apps. User apps. No change. As usual, that we have direct communication. Okay, here direct communication. No change. Direct execution of user request. Now there is a modality. The modality is like this. Here, the part of VMM, the part of VMM is isolated in a manner like root mode privilege levels, means privilege instructions only. Privilege root mode privilege levels. Now again, see, this is a one-step communication, and as usual that we have the communication from VMM to hardware. See, it seems like binary, but not. As I told you, we call it here is OS requests, operating system requests trap to virtual machine monitor without binary translation or para-virtualization. So there is no concept such as the binary translation or para-virtualization is involved here. So this is a different topic. In what sense? Why? Because here the VMM instructions are considered as only root level or root mode privilege levels instructions. So these kind of communications can, these kind of instructions can have and the communication with host operating system and can manage the preferences of kernel operations of guest operating system. So let me illustrate the concept in a very clear cut. Okay, this is the difference. Now let me place here. As usual, the hardware, here I have mentioned these are the root mode privilege levels, no, and from this ring 0 level here, ring 3, this one till this point, these are non-root mode privilege levels. These are non-root mode privilege levels, means not privileged instructions, non-critical instructions or critical instructions, both. But here completely not. So the instructions or the requests coming from ring 0, ring 1, ring 2, ring 3 are completely non-privileged, non-root mode privilege levels. So this is very easy to access. But here the possibility is given from the VMM where only the root mode level privilege instructions can be executed on the host operating system to manage the activities of other applications. So I'll discuss. Hardware vendors are rapidly embracing virtualization and developing, say, new features to simplify virtualization techniques, my dear. See, first generation enhancements include Intel virtualization technology. You might have remembered. The first generation enhancements include Intel virtualization technology, say, that is called virtualization technology with VTX. I'll discuss this one, no? And other type of I could remember, that is AMD. AMD is AMD V, like which both are target privilege instructions with a new CPU execution mode feature that allows the virtual machine monitor to run in a new root mode below in a new root mode below ring 0. Below ring 0. See as shown in this figure, privileged and sensitive calls are set to automatically trap. Privileged and sensitive. Okay, privileged means from here, sensitive means from guest operating system. So privileged and sensitive calls are set to automatically trap the hypervisor, removing the need for either binary translation or paravirtualization. We have removed these two concepts. So the guest state is stored here. Okay, guys, the guest operating system state is stored in virtual machine control structures. So we'll call this as VTX, virtual machine control structure VTX, or virtual machine control blocks. This is AMD virtualized, AMDV. So processors with Intel VT and processors with Intel VT and AMDV became available in 2006, I believe. I could remember. Yeah. So only newer systems contain these hardware assist features, right? So due to high hypervisor to guest translation overhead and a rigid programming model, virtual machine VMware's binary translation approach currently outperforms first generation hardware assist implementations in most circumstances. So the rigid programming model in the first generation implementation leaves very little room for, say, software flexibility in managing either the frequency or the cost of the hypervisor to guest transition. So because of this, VMware only takes the advantage of the first generation hardware features in limited cases, such as for 64-bit computers. I'm using my workstation now, that is 64-bit. 64-bit gets support in Intel processors. So in this way, the concept of binary translation, operating system or assisted virtualization or paravirtualization, and this one, which one? That is hardware assisted virtualization concepts have been discussed. Okay, in this way the concept has been proposed for an efficient processing of instructions. Okay, time by time, in order to manage the execution process of execution process of various applications permissible. Then only the concept of cloud became that is paper use demand, and as I told you, no, that is the way. So that's why the people who have established the infrastructure service became even millionaires and billionaires. Right? You won't believe, my dear friends, even the mechanical student or non-CSE background student can create wonders, and still such kind of students are working with the hardware specific corporations like Intel and others. Okay, so this made us this situation made us utilize the latest and latest technology in all the way. Okay, so this is about the actual thing happening with the cloud, and cloud offers these three types of means the complete cross 86 virtualization, right, for better service. So apart from this, apart from the hardware CPU assisted virtualization, what we have we have memory virtualization. One, where is my memory virtualization and IO virtualization, device and IO virtualization concepts and all. So I'll discuss this device and IO virtualization concepts by extending the concept of say paravirtualization of architecture to some extent, probably with hardware support for virtualization. With just now I discussed the Intel concept, that is VTX and AMDV virtualized 64-bit. No, this architecture I'll discuss. Okay, fine. Yeah, okay. Any issues? And by today, mostly the strength of this class has been fixed. So from tomorrow onwards, again, then even I have recorded your attendance. Then from tomorrow onwards, especially for BTech that I have deployed one of my scholar, for MTech and for PhD I have deployed one of my scholar, and for other students that I have deployed one of my scholars. So these three will come and they will monitor your regular participation, means attendance, and accordingly I'll try to update and upload the attendance in the MIS. Fine. So I'm very much clear from my end, my dear friends. So be careful, and as usual, do this is a give and take policy that so you have chosen this subject for knowledge. Say I'll be happy except the BTech students. Why? Because they won't mind. Why? Because they join company and they themselves means treat like this blah blah blah. Okay, so I'm not commenting here. Means they became fully professional now. They won't think and they won't think much about this one. So especially they who want to gain the knowledge in this subject for future updations in the form of software as usual. Please follow the same. Okay, so please do let me know that if you have any concerns from your end. Otherwise, then we'll conclude the class. Fine, then it seems like you don't have any queries from your end. Yeah, sure. By tomorrow morning, I'll share. Okay. Yeah. Okay. Then. Fine. Bye, guys.